So let me try to recall the setup that we are dealing with. We have P compact metric space, G skew product of the form x v goes to f of x gx of v. Gx is just our linear map acting in projective space. And we have a function phi which is phi of x v equals logarithm of ax of v divided by v. And we prove the proposition to the effect that so we proved that these limits I of x so these limits exist mu almost everywhere. And there exists G invariant probability measures eta I and eta S projecting down to mu. So we have M cross P, and we have this canonical projection to the first coordinate, and this means that if you take any of these two measures here, eta I or eta S, and you project them, what you get downstairs is mu. such that the integral of phi d mu d eta I is equal to the integral of I d mu, and the integral of phi d eta S is the integral of S d mu. Okay, so this we proved already on last week, and then let me just remind you that in the case that we are interested in, this situation, this is just lambda minus of x, the smallest exponent, and this is lambda plus of x. Then as a corollary, we obtained the following statements for mu almost every x. There exists vi of x and vs of x such that the limit 1 over n sum phi gjx v I of sx is equal to I of x, and the same limit for the other vector. Is s of x. Okay. And this means, so this here is lambda minus, this is lambda plus, and here on this side what we have is the lambda of x vi of x, and this is lambda of x vs of x. Okay. So what we are saying here in this corollary is at each point there exists some vector vi whose rate of growth is is lambda minus, and there exists some vector whose rate of growth is lambda plus. Okay? These were defined as the rate of growth of the norm and the conorm, and I'm saying that they are realized by some vectors. Okay? Also, at least in these for these vectors, I'm saying that the limit exists. Limits exist, which is the kind of statement that we want to obtain. So, in a sense, this is a restatement or another corollary. And now this is formulated for linear cocycles. The limit, I called it a proposition. It's a consequence. If x goes to vx is a measurable f invariant subbundle, then limit 1 over n log of the norm an of x restricted to vx so this expression is lambda plus of x this is lambda plus for the cocycle for the restriction. This is a great growth of the norm for the restriction to Vx. So these two limits for the restriction of the cocycle to this invariant subbundle exists, well, and they are precisely the minimum of all lambda x v with v in Vx and the maximum. Okay. There's really not anything that I have to do to prove this proposition because it's already here. The rate of growth of any vector is this is obvious. This is obvious. The rate of growth of any vector is less or equal than lambda plus and is bigger or equal than lambda minus. Okay, this is how the norm grows, and that's the soup of all the growth. This is the minimum, the inf. So this is always true. Always. Here, we are proving in an abstract setting that the infimum is attained and the supremum is attained. There exist some vectors where the rate of growth is the minimum and where the rate of growth is the maximum. So the corollary says that both equalities are attained. There exists some vector where you have this equality and some other vector where you have this equality. Okay? We can do this by letting V vary in the whole space, or we can do that for V only in this restricted to this invariant subbundle. So we get the conclusion of the proposition. Okay. Any questions? I don't want to be too boring, too repetitive, but I can, if there's any doubt, I can. Here, in fact, we are. If we want to restrict to a subbundle, we have to use projective space for that subbundle. Okay. Of course, this, by our notation, this is what we call lambda 1. Well, as a consequence, as a corollary of this proposition, we get that lambda plus of x is lambda 1 of x, and lambda minus of x is lambda k x of x. Why is this a corollary? Just take Vx to be the whole space. Okay, then I don't have this restriction here. And then the minimum is over all vectors, the maximum is over all vectors, and that's precisely what lambda 1 and lambda k are. This is more than a corollary, it's a special case of the statement. The special case where the subbundle is the whole RD. Sorry? Yeah. Yeah. This is the maximum and this is the minimum. For some reason I lost a few pages of the proof. Let's see, are we able to do this? So at the very end of last lecture, we were dealing with the following proposition. So let x be measurable f invariant subbundle and alpha beta be measurable functions, invariant measurable functions such that algum de vocês imprimiu? Ok, better look. Want to be sure. Yeah. So, okay. So we have this these two conditions, 1 and 2. And then, so I will start the statement here. And here is an interesting observation. This condition here implies that the limit 1 over n log the norm is less or equal than alpha of x. Observation. So I'm considering a situation where I have a vector subbundle, and the assumptions are that the rate of growth inside the subbundle is less than alpha, outside is bigger than beta, and alpha is smaller than beta almost everywhere. So vectors inside V grow slowly, vectors outside V grow fast, and this observation is an immediate consequence of this proposition, because what is here, what is written here, is lambda plus restricted to V, right? This is the growth of the norm of the restriction to V, and by the proposition, that is the same as the maximum growth of vectors in Vx. I'm using this fact here. Lambda plus restricted to V is the maximum growth of any vector in Vx, and by assumption, that is smaller than alpha. Okay? So if all vectors grow slowly, the norm also grows slowly. So what we do is that we write A of x as a matrix, as a kind of matrix, B of x, C of x, 0, D of x. This is the expression with respect, the expression of these matrices with respect to the direct sum decomposition. Rd equals Vx orthogonal plus Vx. Okay, we have this, we have Vx orthogonal. I'm going to write, I'm going to draw it like this to stress the fact that by assumption Vx is invariant, but the orthogonal has no reason to be invariant. So I take any vector here, I apply A of x. This goes to Vf of x, and here I also consider the orthogonal, Vf of x orthogonal. And so the behavior of vectors goes like this. If I take a vector here, blue vector, it is mapped here. And if this is V, then this is dx of V. That's the definition of D. dx is just the restriction of Ax to Vx orthogonal, to Vx, sorry. Now, if I take a green vector, like this one, and I map it by A of x, the image will probably look like this. Not necessarily along the orthogonal, because the orthogonal is not invariant. So I decompose this into two orthogonal components. This one is what I'm calling B of x applied to V, and this one is C of x applied to V. Okay, that's what it means. What this expression means, and the fact that we have a 0 here corresponds precisely to saying that if I take a vector in Vx, it goes to a vector in Vf of x. So with respect to and Rd equals Vf of x orthogonal plus Vx Vf of x. And then the proposition says that the lim sup 1 over n log a n of x applied to u plus v is equal to the lim sup 1 over n log of bn x applied to u. This is for any u in Vx orthogonal and v in Vx minus 0 and v in Vx. So in other words, if you take any vector like this here is u and this is v, this is u plus v. When you apply an at x, you go to well, some vector. You go to some vector. A n of x applied to u plus v. Also, you can take the orange vector u here. You can take the orange vector u here and look at its image. Bn of x applied to u. The image of this vector by the matrix Bnx applied n times, and this this statement says that they both grow at the same rate. The rate of growth of this iterate under A is equal to the rate of growth of u under Bn of x. Okay. Moreover, one limit exists if and only if the other one exists. One limit exists if and only if the other one exists. I am not saying that this is the projection of that. Okay, it's not true. But they grow at the same rate. As I said last time, this is something that one can believe without looking at the calculations. The calculations are short and not very interesting. But one can believe this because of the assumptions. What these two assumptions say is that vectors in V grow slowly, vectors outside V grow fast. So if you take a sum of the two, you will have a small term and a big term. And in terms of the exponential rate of growth, the big term determines the exponential rate of growth. So I'm saying here U is the main guy. The rate of growth of U is going to determine the rate of growth of U plus V, because this one is going to grow slowly anyway. Okay? So I think we can believe in that without actually checking the calculations. But it's half a page calculation anyway. Okay, so now we are getting close to the end of the proof. And well, I actually lied. It's 2 pages proof. It's not half a page, but still, it's not an interesting proof. One uses things like this, which are written down as exercises. One uses the following kind of property. If AN and BN are positive sequences of positive numbers, then the lim sup of 1 over n log AN plus BN is equal to the maximum between the lim sup of 1 over n log AN and 1 over n and the lim sup of 1 over n log Bn. And similar properties for for example, lim sup of 1 over n log of the square root of an square plus bn square is the same. Okay. So that's what I was saying. And that's in precise terms what I was saying. If you have one vector that grows slowly and another one that grows fast, the sum, the rate of growth of the sum is determined by the one that grows the fastest. Okay. So let us finish the proof, and that's not very, doesn't take very long. Now, so we want to finish the proof. So what we want is to prove that the limit 1 over n log ANX V exists for mu almost every x and every v. Okay, this is what we have been after since the very beginning. Every v different from 0. Now we already have the flag Rd equals v1 of x, which contains v2 of x, and so on. This was already defined very near the beginning of the proof, actually. And and we already know that, so we already have this, and we know that if v belongs to the difference between two of these, then the lim sup is equal to lambda I of x. This we did at the very beginning. Okay? This is very soft. The problem is here that we want this lim sup to become a limit. And we do that as follows. We do that as follows. Take Vx to be this subspace here, this subbundle. Okay? So the proof of this will be by starting from the smallest rate of growth and moving upwards for larger rates of growth. Okay, so I'm starting with the very smallest subspace. Now, there's a little very annoying thing is that the dimension of this subbundle may vary. That's always annoying. And another annoying thing is that k of x, the number of subspaces, may vary as well. So let me do a little bit of bookkeeping to avoid that. Up, since the k is invariant, k is an invariant function. It's constant on orbits. So if you have a certain value of k at point x, you have the same value at f of x. And the dimension of this subspace is also invariant. We can always take our space, M, and we can decompose the space into a certain number of subsets such that on each we can decompose M into invariant subsets like this one, where k is constant and the dimension of vkxx is constant. Okay, just fix the values I want for the k and for the dimension, and then I have the set of points where k takes this value and the dimension takes this value is an invariant subset. And of course, it has these properties. Okay? So how many of these sets do I have? K is in between 1 and D, the dimension of the space. And the dimension of Vk, the dimension of any of these subspaces, is also between 1 and D. So the number of possibilities is finite. So into finitely many, okay? Now, what I can do is I take the restriction of my co-cycle to each one of these invariant subsets. I take the restriction of f and f to these to each one of these subsets. We may suppose that k and the dimension of the corresponding subspace are constants. In other words, it's annoying that the dimensions may vary and the number of subspaces may vary, but it's a very minor annoyance because we can always do this by restricting to a certain finitely many subsets. We may suppose that they are constant. So from now on, I assume that k is constant. Okay? I'm going to use this proposition with this choice of the subbundle. It's a measurable invariant subbundle. I have to say which alpha and which beta I want to take. And I will take alpha x equals lambda k of x. Okay, so notice that lambda x v is less or equal than alpha of x for every v in vk, because that's the definition of vk. And I take beta to be the next one, the next Lyapunov exponent, minus 0. And then for all the other vectors, the rate of growth is at least lambda k minus 1 for every v in Rd minus Vxk, because that's the definition of Vxk. This was defined as the subspace where the rate of growth is minimum. Okay? So we have the kind of situation that I spoke about. Okay. So one of the propositions that I wrote, unfortunately I don't have the numbers anymore. It's actually a little bit better than this, right? Because here is equal. Vk is the subset of points where the rate of growth is equal to lambda k. It's essentially what is written here. It's what's written here. In the case I equals k, what we have is that if v belongs to vx k minus 0, k plus 1, then the rate of growth is lambda k. Okay, so this is equal. Good. Now, this fact here implies that the limit of the norm 1 over n log a n x restricted to vxk. Remember, this was the maximum of all lambda x v in vxk. But all v's have the same lambda. So this is equal to alpha of x. The same property implies that the limit 1 over n log a n x vxk conorm is the minimum of this expression, and both the maximum and the minimum are equal to alpha of x. Okay. This is one of the propositions that I had written here. The norm grows as the largest Lyapunov exponent. The conorm grows as the smallest Lyapunov exponent. And for this subspace, for Vk, the largest and the smallest are the same, because it is formed by vectors with one single well-defined rate of growth. Okay. Now, this has a consequence. If I now look at 1 over n log of a n x v in vx minus 0, a unit vector, say. If I take any vector in vx minus 0, this is smaller than 1 over n log a n x restricted to vx, because the norm is the largest expansion, and it is bigger than 1 over n log of a n x v, the conorm, for the same reason. Okay? For any vector in this subspace. However, I have just explained that this sequence, this is Vk. I have already explained here that this sequence converges to alpha of x. And I also explained that this other sequence converges to the same alpha of x. Okay? So morally, now I'm telling you the secret, how we prove that the limit, at least the first part of the secret, how we prove that the limit exists. The limit exists for the norm and the conorm because they give rise to sub-additive and super-additive sequences. And for sub-additive and super-additive, we can use the sub-additive ergodic theorem that says that the limits exist. So this limit exists and this limit exists. In this setting here, for this particular subspace, I even get that the two limits are equal. So by whatever this is called, the limit 1 over n log of a n x v exists and is equal to alpha of x for every vector v in vxk minus z. Unit vector. Doesn't matter. Okay. It is obvious that taking unit vector is no restriction. If you multiply a vector by a constant, it doesn't change anything that I say. You can always normalize. So you see, I want this for every vector v, and I already succeeded in doing that, at least for the vectors that are inside this subspace here. Okay? And it's a nice argument where you use the norm and the conorm to bound the growth of the vectors. And for the norm and the conorm, we know that the limits exist. And for this subspace here, they are the same, so it follows that the limits exist for every vector. Okay? Now this is the first half of the proof, and now the second half, first half of the end of the proof. So now we write RD as Vx orthogonal plus Vx. We're going to deal with the other, the rest of the spectrum, and we write A of x as B of x, C of x, D of x. And we want to prove that the limits 1 over n log a n x u plus v exists. So what is u plus v? U plus v means any vector here. U in this component and v in this component. We want to prove that this exists. We already know that the limit exists for vectors that are here. We want to prove that the limit also exists for the other vectors. The other vectors are vectors of this form for any u in Vx orthogonal and v in Vx. If I write this, I mean all vectors in Rd. I don't need to do that because I already have the statement for vectors in Vx. I only have to consider the ones in the complement, and that means that I have the right to take u non-zero. Okay, so in order to prove this, we want to prove it for every vector in Rd minus 0. We already have the statement for vectors that are along Vx. Vx equals Vxk. Now we want to have the same for the other vectors. And the other vectors may be written as a sum like this. Well, it is here, right? I know that the lim sup by this proposition, this limit exists if and only if this other limit exists. We know by this proposition that this happens if and only if the limit 1 over n log bn x u exists. Now what is Bn? Bn of x is a map, a linear map, from Vx orthogonal to Vf of x orthogonal. This defines a linear cocycle on it defines a linear cocycle just by the restriction. No, it's not the restriction because B is not a restriction, but it defines a linear cocycle like this, where you take x and the vector v in Vx orthogonal, and you map it to f of x, b x of v. Okay. Now, the one thing I'm not quite able to write down here is what is the domain of this linear cocycle. The domain is the set of points x, v, such that v belongs to Vx orthogonal. Okay. And now this is a rather unpleasant situation because I always define linear cocycles on product spaces. Okay, and this is not a product. This subspace here depends on x. Okay. One thing I know, the dimension of Vx orthogonal is equal to d minus the dimension of Vx, Vxk, and this is a constant smaller than d, strictly smaller than d. Okay, so if what I would like to say, the way I would like to finish the proof would be by saying we have a cocycle defined on a subspace whose dimension is strictly smaller than d. So by induction on the dimension, I may assume that this limit exists. By induction on the dimension of the vector subspace, the vector space, we may assume that the Ocellades theorem holds for this cocycle. So the limit 1 over n log Bn x u does exist for almost every point and every u. And so that ends the proof. Okay? This limit exists if and only if this one exists. And this one exists because now we are working with a cocycle on some place whose dimension is strictly smaller. So we may use induction. Okay? Now, everything I said is honest. But to make it more transparent, I have to say two things, two simple observations. So, two observations. Observation 1 has to do with this question of the dimension, with this difficulty here, that I don't have a product. However, it doesn't matter, because the dimension of Vx orthogonal, so Vx orthogonal is a measurable subbundle with constant dimension. L, smaller than D. Measurable means that we can find a basis x1 xl of d of x, a basis of Vx orthogonal, where all these functions are measurable vector fields. Okay? And once we have this, we can identify Vx orthogonal with RL measurably. Once you have a basis for your subspace, you can use the basis to say it's isomorphic to RD. You just do RD, RL to Vx orthogonal, sending alpha 1 alpha L to alpha 1 x1 of x alpha L xl of x. Okay, so we can identify each one of these Vx orthogonal with RL, and then the subset, the subset xv is identified with M cross RL. Okay? So it's completely irrelevant whether it is a product or not, because once it depends on a measurable fashion, you can make a change of coordinates and transform this into a product. Yeah, you so you have Vx orthogonal goes to V f of x orthogonal, and this is Bx, right? You have here an identification to RL through the basis x1, xl. Here you have another identification with RL. So this one is through this basis. This one is through this basis. Okay. And then you have a map here, which is just B of x seen written in this basis. It's like you take this matrix and you change the basis. So you have here another map, B hat of x. And now the cocycle that I'm talking about there is the cocycle that goes from M cross RL to M cross RL, sending x v to f of x b hat x of v. This is just that one in new coordinates. Okay? Of course, you could wonder, well, but when I change the coordinates, what happens to the norm? The norm is important because the norm is used in the calculation of the exponents. What happens to the norm? So maybe I'm changing the norm and I'm changing the exponents completely. Well, that's not a problem. Once you have a basis, you can always use Gram-Schmidt to make it an orthonormal basis by Gram-Schmidt. And if this is an orthonormal basis, this identification is isometric. And so the norm doesn't change. Okay? I could also say, well, we are in finite dimension, all norms are equivalent, something like that, but this is even quicker. Okay? The other observation is the following. We may assume that the Oscilladet's theorem holds for this cocycle. Well, the Oscilladet's theorem has a hypothesis, has assumptions on the cocycle. I have to check that those assumptions hold for this cocycle in order to be able to apply the Oscilladet's theorem. So here, we may assume we have to check that the assumptions are that the logarithm of b x and the logarithm of bx inverse are integrable. Assuming that this is true for A. Well, I think I can convince you that this is more or less obvious just with a picture. Remember, A of x is B 0 C D. And basically, the reason is that you take a vector u in the orthogonal, you iterate it by A, it goes somewhere, and then you project it to the orthogonal, and what you get here is Bx of u. Okay, that's the definition of B. Take a vector here, map it by A, project it down to the orthogonal. This is Vx orthogonal, and this is Vf of x orthogonal. Now, everyone knows that when you take any vector and you project it, the projection is smaller, right? So the norm of Bx is less or equal than the norm of Ax, restricted to Vx orthogonal, which is less or equal than the norm of Ax. Okay? So if the log of A is integrable, this is smaller, so this is integrable. Okay? You have to notice that this has to be checked, but checking it is very easy. Okay? So this implies, so log plus of A integrable implies log plus of B integrable. And that lets you think about the statement for the conorm. Okay? So this is how we prove the Oscilladet's theorem for non-invertible transformations. The first part is very soft. The second part is about proving that the limit exists, and it combines using invariant measures with using the subadditive ergodic theorem to prove that the limit exists for the norm and the conorm, and then this kind of a sandwich argument, and plus induction on the dimension. Okay. I'm not going to prove the theorem for invertible transformations because that would be an overdoses of Oscilladets. But let me just say what we have to do. The only thing that is missing for the to get the invertible version of the theorem is the following: you have Vxi, you have Vxi plus 1, which is smaller. One has to find a subspace here, orthogonal, transversal to Vxi. We have to find a subspace which is complementary to Vxi plus 1 inside Vxi in such a way that this is invariant. Okay, and that's how we obtain, by taking I equals 1, we get E1, by taking I equals 2, we get E2, and so on, and that's how we obtain the Oscilladet splitting. Okay. I mean, I can do that if you want, but I think we are a little bit overdosed with the Oscilladets. Okay, Marcelo. Any questions? It's not true in general. I mean, it's not continuous for sure, and And I don't know of any modulus of regularity better than measurable that is known to hold it in all cases. And it's not that we need to look for pathological examples to, I mean, even simple examples don't have better than measurability.
Is that the choice of pH orthogonal doesn't play a big role, right?
No.
Any complementary subspace?
Yeah, in principle, any. The only place where it had a role was here, when I said when you project, the projection is smaller. But if you do anything with an angle with respect to the x that is bounded, it's just the same. Or even not bounded, but not too crazy, it's just the same. In a sense, what one would like to do would be to project to EI of x, except that if you have a non-invertible map, this doesn't make sense. And maybe I can spend the rest of the table with a few remarks around this instead of starting a new subject. You see, in the non-invertible setting, this is a simple idea, but it's an important idea. We get this flag. And the flag is defined by the fact that if V belongs to VI x, then the exponent of V is small, is smaller than, so it grows slower than any for any other vector that is not in Vxi. So these vectors grow, the subspace Vxi is such that if you take a vector inside, it will grow slowly, whereas all the other vectors outside grow faster. So outside, there's no way we can tell the difference between any of these vectors in terms of growth, because they all grow at the same speed. And there's a very elementary situation where you can see this that helps understand a little bit of what is going on. Suppose you have a linear map like 2, 0, 0, 1 half acting on R2. This is the most elementary example where you get this kind of situation. So if I ask you, what is the limit of 1 over n log of an applied to V? So you see, this is simpler because it's only one matrix. And what do we have? So this is an eigenspace with eigenvalue 2. This is another eigenspace with eigenvalue 1 half. And for instance, if you take a horizontal vector, of course this is log 2 if V is horizontal. Right? If you take a vertical vector, then of course you get a completely different answer because it will be contracted. So it will be minus log 2 if V is vertical. Right? What about the other vectors? It's not in between. the other vectors, as you iterate, their vertical component goes to 0, their horizontal component grows, and the largest component determines what happens to the vector. So if for any other vector, the rate of growth is still log 2. So I'm going to erase this, and I'm going to write not vertical. Okay? So you see, if I give you this matrix and I let you calculate how it acts on vectors, you are able to compute the vertical axis because it's the only direction in which vectors are contracted. But you are not able, just by looking at this, you are not able to detect the horizontal axis. Okay? You are able to detect the contracting eigenvalue. You are not able to detect the expanding eigenvalue. Now, how could you detect the expanding eigenvalue? Any suggestions? Well, instead of looking at the limit as n goes to plus infinity, you can look at the limit as n goes to minus infinity. And then you get, the roles are interchanged, and you get to detect the other subspace. So that's a little bit what is going on here in a more sophisticated situation. When we iterate forwards, we only get a flag because we can only, iterating forward, we can only detect small expansion. We cannot say which vectors are we cannot distinguish those vectors that are growing fast, only those that are growing slowly. In order to get that, we have to iterate backwards, and then we need the transformation to be invertible. That's why the second theorem, the invertible theorem, is more detailed and that gives more information. There's another observation that is perhaps interesting to mention. Suppose I consider two vectors. So I'm still in this same setup. Suppose I consider three vectors, v1, v2, and v3, linearly independent vectors. Okay, and I consider the parallelogram that they define. I want to know what happens to the volume. This parallelogram I'm going to call P. What do we know about the volume of A, X, and P when n goes to infinity? Say plus infinity. What can we say about the volume? Why am I interested in this? Well, it is interesting in itself, but in a sense, it's the obvious it's an obvious generalization of something that we have been saying. We have been looking at one vector and asking how its norm grows. I'm upgrading the kind of object that I look at, two vectors, three vectors. I look at the linearly independent, I look at the parallelogram that they define, and I want to know how the volume grows.
Why do we start from dimension 3 and
Just as an example. Just an example. I want to practice my 3D pictures. This is, it won't make any difference how many vectors. Now, what can we say? Well, the volume of a parallelogram can be calculated using the length of the edges and then angles. Okay? So this is the length of the product of the length of edges, and then some expression that depends on the angles between these vectors. In dimension 2, the simple situation, it would be the sinus of the angle. In dimension 3, we have to think a little bit, and I don't want to think. It's something that depends on the angles. Okay? Now, this thing here grows like e to the n lambda how am I going to call this? Theta 1, where theta 1 is just the Lyapunov exponent for the vector v1. Theta j is the Lyapunov exponent for vj. And of course, then we have similar expressions for this. Okay. And then we have the angles. And when we say the angles, it's not the angles here, it's the angles in the image. Okay. Now, first warning, the angles, when you iterate like this, the angles are not bounded from 0. Of course, they are bounded from above because the angles are always less than pi over 2, but they are not bounded from 0. What we have in the invertible Euclid's theorem is that the angles decay exponentially. All the angles decay exponentially. What do I mean by all the angles? In this example, I mean the angle between a n x v1 and v3 and v2, this angle, also this angle, also this angle, but not only that, any possible angle that you can think of. For instance, the angle between a n x v1 and the plane, this angle to the plane defined by a n x v2 and a n x v3. Okay. Not only between vectors, but also between any pair of subspaces spanned by these vectors. All these angles decay exponentially, sub-exponentially. Decay sub-exponentially. Sub-exponentially means that the limit 1 over n log of the angle goes to 0. Okay? So in this parallelogram, the angle between, say, the two vectors in the base is sub-exponential. Sub-exponential means that for any epsilon, this is the same thing, for any epsilon, the angle is between e to the n epsilon and e to the minus n epsilon for all large n. Okay? So the angle between the two vectors in the base is sub-exponential. The angle between the base and the other third vector is sub-exponential, and so on. So this means that this expression here, this implies that this expression here is between e to the minus n epsilon and e to the plus n epsilon. Maybe not the same epsilon, maybe 5 times epsilon, but it's sub-exponential. Okay? So the angles can go to 0. When the angles go to 0, the volume is not so well related to the product, the volume of the parallelogram is not so well related to the product of the lengths of the edges. But the mistake is of this type. Okay? So if I take 1 over n log of the volume, it goes to theta 1 plus theta 2 plus theta 3. Okay? Of course, that depends on the values of theta 1, theta 2, and theta 3, which depend on the positions of the vectors. So if I ask you, choose any parallelogram, make these parallelograms rotate in the way you want. What are the possible values of this limit that you can get? Well, the answer is the possible values are the possible sums of 3 Lyapunov exponents without the right to repeat, because the VI's are linearly independent. Otherwise, the parallelogram doesn't make sense. Okay, let's make a concrete example. So, suppose we are in dimension 5. Suppose we are, suppose d equals 5, and our decomposition is ex1 plus ex2 plus, I'm working the invertible situation because otherwise it doesn't make sense to speak of angles. 3, where this has dimension 3, this has dimension 1, and this has dimension 1. Okay, so what are the possible values of the limit 1 over n log of the volume of a n x p, where p is formed by 3, it's a 3-dimensional parallelogram. What are the possible values? This corresponds to Lyapunov exponent lambda 1, this is lambda 2, and this is lambda 3. Of course, we can have one possibility, is to have lambda 1 plus lambda 2 plus lambda 3. If I choose one vector in this direction, one vector in this direction, and one vector in this direction. What else? Well, I could choose all of them inside this, right? Since this is 3-dimensional, there's enough room to squeeze in a parallelogram of dimension 3. So another possibility would be lambda 1 plus lambda 1 plus lambda 1. What else? I could put two of them here and another one here, or two of them here and the other one there. And that's it, right? Lambda 1 bigger than lambda 2, bigger than lambda 3. So you're considering, this is the case where P is dimension 3. Now you're considering P of dimension 4? Yeah? So what would be the result? Not linearly independent. This is complaining. He's right, but I'm also right. It's complaining. Let me give us a simpler example to draw. In dimension 3, this is the kind of example that you are worried about. We are in dimension 3. Each one of these has dimension 1. And we take a parallelogram formed by vectors that are not in either of the. So they all grow in the future as at lambda 1. Right? So it would seem that the rate of growth would be lambda 1 plus lambda 1 plus lambda 1. Yeah? Well, the reason is that I didn't explain it very well. When I said all the angles, I meant all the angles between Euclidean subspaces, not iterates of vectors, between Euclidean subspaces. I can if there's enough dimension. Okay, that's why I said here we could take three of them here. I can put a parallelogram. This is three-dimensional. I can put a parallelogram which is three-dimensional inside. But of course, we can also take vectors that are not in the Euclidean subspaces, and then the argument that I presented here is false, because the angles that I spoke about I had in mind angles between Euclidean subspaces. Angles between vectors don't. This is not true for iterates. So first of all, for this example, my argument is not correct, and that's why we don't get this. Okay. Now, how can we fix it? We can fix it by relating this parallelogram here to a parallelogram, this one, to a parallelogram whose another parallelogram, P prime, whose sides are inside auxiliary subspaces. Somehow, I'm going to explain that, but somehow deform this parallelogram, construct another one whose sides are inside auxiliary subspaces. And then, of course, one in each subspace, because there's not enough room. Okay? And then my previous calculation can be done. It tells you that the volume of the iterates of P prime grows at rate lambda 1 plus lambda 2 plus lambda 3. And so the volume of P also grows at rate lambda 1 plus lambda 2 lambda plus lambda 3. Okay? So relate to another subspace, another parallelogram where my calculation can be done. Yeah, that's what I have to explain. That's what I have to explain. In fact, I was going to do that, but I was not aware of this motivation. This is a good motivation. Now, there's a, let me try to do that quickly. It's written down. There's an algebraic construction called exterior powers of RD you take any k between 1 and d. In this example, in this construction, k would be 3. It's essentially the dimension of the parallelogram. You take and you consider linear forms, linear functionals, k linear function, alternate k linear maps phi from Rd k times to R. This I'm going to call lambda k of Rd. It's the set of alternate k linear functionals in Rd. K linear means linear in each one of the coordinates, and alternate means that if you change the order of two consecutive coordinates, you change the sign. Examples. For k equals 1, lambda k of Rd, lambda 1 is just a set of linear maps which is R D. So this is a vector space, and the dimension is not difficult to calculate. I think it's combinations of k to the d. Okay. For k equals d, you are taking alternate d linear forms in Rd. You probably remember your linear algebra course when you learned that there exists essentially only one d alternate functional. That's called the determinant. So lambda d of Rd is multiples of the determinants. Okay. Let me give concrete examples of such alternate k linear forms. For example, for k equals 2, if you take phi 1 from Rd to R linear, phi phi2 from RD to R. You can, from this, you can define a two-linear form as follows. So phi is a bilinear form. It has two vectors, u and v, u1 and u2. Okay, given a pair of linear maps, linear, you can construct an alternate bilinear by doing this. Phi of u1, u2 is phi1 of u1 times phi2 of u2 minus phi 2 of u1, phi1 of u2. Okay, we write phi, we say that phi is the product of phi1, phi2. This is the usual product for linear forms, for differential forms, etc. Okay. More generally, for any k, given phi1, phi k linear, we can construct the product and it's just the obvious generalization is the sum of phi1 u sigma 1 phi k u of sigma k. The sum is over all permutations, and you multiply by -1 to the sign, to the parity of the permutation. Okay? So this is a special element of observe that lambda 1 is the same thing as RD. Lambda 1 of RD. It's the dual, and the dual, you can identify the dual with RD itself. Okay? So the elements of this form are called decomposable k vectors. And the elements of lambda k are called k vectors. So when I write a parallelogram, when I consider a parallelogram v1, v2, v3, I can view this as a three vector, v1, v2, v3, where I'm using this identification. Identifying RD with its dual. You choose one identification once and for all, and then three vectors I may think of as three linear forms, And the parallelogram they form, I may think as corresponding to a certain this expression. Now, lambda k RD is a vector space. And it's possible to give it a natural norm. It has a natural norm. Such that there is an elegant definition of the norm, an elegant formula, but I'm not going to write the elegant formula. I'm going to tell you just what the norm is for a decomposable, such that for decomposable k vectors, so if I have a decomposable k vector, its norm is equal to the volume of the parallelogram. Defined by V1 through Vk. Okay? Now, to finish, because I don't want to go too much over time, we can write V1 as a linear combination of UI, V2 as a linear combination of UI, V3 is a linear combination of these ones, with UI in EXI. Each of these vectors may be written as a linear combination of vectors in E1, E2, E3. Then V1, V2, V3, my parallelogram, is a sum of U1, U2, U3, just use linearity with a certain coefficient here that we can calculate. Just do the calculation. Okay? So here I'm relating the original parallelogram to another parallelogram whose sides are contained in auxiliary subspaces. Okay? For this, I can see how its norm, its volume grows. And for this one, you have exactly the same rate of growth because there's just a constant here. And for this, my calculation works. No, because by linearity. Just by linearity. Okay? So any parallelogram, any k vector, may be written as a multiple of k vectors whose edges are contained in the auxiliary subspaces. And that's what I had in mind, but I didn't spell out earlier. So when you do this calculation, you only have to look at k vectors that are already inside, and then you can take advantage of the angles. Okay, this is written in the book more carefully than I had the time to do here.